Alright, physical geology class. This is chapter 11 lecture on earthquakes and earthquake hazards. An earthquake, if you've ever felt one, it's pretty scary. It's when there's ground shaking, which is caused by rapid movement of tectonic blocks or blocks of rock that fall along a fault. Okay, and as they slide past one another, the fault remains locked. Okay, and then every once in a while, there's a bit of a slip and motion occurs, and that's what causes the kind of ground shaking. Okay, most earthquakes occur along pre-existing faults, and the faults are locked, meaning that the surfaces themselves, they're like stuck in position because of frictional forces, and a lot of times the faults separate two tectonic plates, and those plates are in motion and they want to move, so they apply stress to those fault surfaces, and when those stresses exceed the frictional forces holding the faults together, that's when you get a sudden displacement of or this movement, and then that movement's accompanied by energy being released by the earthquake. So the slippage originates underground, and we call that the focus or the hypocenter. Okay, the epicenter is what you typically hear reported on the news. That is the spot on the surface of the earth directly above the focus. Okay, and then the energy that's released from the sudden movement or displacement, it's released as energy waves, and we call them seismic waves, and they radiate in all directions from the focus. So here's the hypocenter, here's the focus, and then this is where the slippage begins along the fault plane, and here's the fault plane. Okay, so here's block number 1, here's block number 2. They're in motion. Block 2 is moving up, block 1 is moving down. Boom, there's an initial slippage down here, and then the seismic waves propagate in 3 dimensions away from the hypocenter through the crust. And then the epicenter, as you see, is the spot directly above the focus. And we worry about the epicenter because we have buildings here, and cities and people. And so that's when we feel those seismic waves that travel through the Earth's crust. So the energy released from earthquakes can cause volcanic eruptions, landslides. Okay, other geologic events can create a lot of energy propagating outwards, like volcanic eruptions, like meteorites. But essentially earthquakes, they continue to happen, and they'll continue to happen into the future. Stress builds up along these fault planes because of plate tectonic movement. And as that stress overcomes the frictional resistance, then there's a slip and an earthquake is created. You can kind of visualize this in the next slide. We like to call this elastic rebound, and the rocks kind of initially deform, and then they snap back to their original positions after there's some displacement. Okay, here's an example of the amount of displacement after an earthquake. Here, this is in California. This is somebody's, orange grove. And if this farmer had OCD, this is a major issue, because here's the fault line, and it displaced the rows of, crops off a bit. So, yeah, that can be kind of, bothersome. Here you can actually measure the displacement. Maybe that's about 5 or 4 feet. But this fence was once connected over here, and because of the motion on the fault surface, now there's this huge gap in the fence, and all the farm animals can escape. No. Okay, so this is how it works. Here's the 2 tectonic plates. Here's tectonic plate 1, for example, or 2. It can just be a crustal block. Okay, and they want to move in different directions. Okay, this one is moving in that direction. This one is moving in the opposite direction. Okay, so here's the fault line. And they can't move because of the frictional resistance. Rocks aren't very lubricated, they get stuck. Okay, and so what that happens is that these land areas start to bulge up and down as the stress builds. Okay, and scientists can actually measure that amount of uplift from the stresses building up. And then once the stress is too great and overcomes that frictional resistance, boom, you get an earthquake. And that's why it's kind of out of focus. Seismic waves are traveling through this entire area, and people will be feeling that earthquake. And then the process repeats itself again. This step here is the same as this one. The only difference is that displacement has occurred. Okay? And this just continually happens over and over again. Stress builds up again, another earthquake, back to a kind of quiet time, and stress builds up over time, and then you get another earthquake. Okay, there are aftershocks and foreshocks, and if you've lived anywhere where there are earthquakes, foreshocks are smaller earthquakes that may occur before a larger earthquake. They kind of foreshadow maybe what's to come. That's not always the case, but if you live in places where earthquakes are frequent, you have to prepare for these things. Like at school, you dive under desks, and they have their protocols. Aftershocks are much more prevalent. Aftershocks are essentially like earthquakes that occur if you have a major earthquake that occurs and there's a lot of slippage along a fault. There's a lot of movement along that entire fault, and the rock blocks are kind of moving into new positions. And as they do so, slippage will continue to happen until the fault kind of settles. And that will release, still a lot of movement occurring, and that'll generate a lot of seismic waves. Okay, so there are a lot of smaller earthquakes after the big earthquake. Okay, over time, the frequency diminishes as well as the intensity. Okay, so I have 3 videos here. Please watch them. They're probably very, very nice videos showing the concepts of aftershocks and foreshocks. I think one's a earthquake in California. Another one shows you the aftershocks after the large earthquake in Chile. So definitely worth the watch. I can't do it in this lecture, but they're there, so you can do them on your own time. Okay, so earthquakes typically occur along pre-existing faults. They can create new faults in certain areas. And so that differential stress causes the crust to break into discrete kind of blocks, and then they start to move. And we've talked about the different types of faults before, but here they are. The normal fault is associated with tensional stress, typically at divergent plate boundaries. These usually aren't very large earthquakes, so anywhere we have divergent plate boundaries in the mid-ocean ridge, there's constant movement there, but the earthquakes generally are not very intense. Okay, reverse or thrust faulting, that's found at convergent plate boundaries, where 2 tectonic plates are colliding with one another. Here in these environments where you can have a subduction zone, they generate megathrust faults, and megathrust faults are the faults that generate the strongest earthquakes recorded on Earth. Okay, they produce powerful earthquakes, and they can even generate tsunamis, which are very dangerous. Strike slip faults are transform faults. All right, they form at transform plate boundaries, and they can cause fairly large earthquakes, not as large as the reverse or thrust faults, but the difference is typically the strike slip fault earthquakes are closer to the surface. So people that live closer to the surface will feel these seismic waves very rapidly, and they can be very dangerous. Some of these transform faults on land can have what we call gradual displacement or fault creep, and that's a kind of almost like a safer way of having the tectonic plates move. So instead of one big movement displacement and a giant earthquake, there'll be numerous smaller earthquakes, and it'll allow the blocks on the fault plane to kind of move slowly rather than really quickly and dangerously. Okay, but there are ruptures, and that can result in major earthquakes. In fact, there's been some really strong ones. Most recently in Port-au-Prince, Haiti, in 2010 there was a really strong earthquake there. Okay, here's an example of a megathrust fault, and what's happening is there's 2 tectonic plates moving towards each other, and the earthquakes occur along the surface boundary of the subducting ocean plate. So here you go. This is where the earthquakes are occurring. And if you notice, that's kind of deep within the crust. Okay, so these are really strong earthquakes, and they're their focuses are very deep, or foci are very deep. Okay. This is an example of a strike-slip fault in California. This is the North American plate that we're on. Okay. And we're moving south relative to the Pacific plate. And much of California is on the Pacific plate, all including LA, San Diego. This whole area is moving northward, and then that creates kind of like a fault zone, right? This is the San Andreas Fault, but there are many faults that kind of radiate away from the San Andreas Fault, and then there's movement along all of these faults. And so major earthquakes can occur along the San Andreas Fault. There was a major one in San Francisco in 1906. In the late 80s, there was one closer to the San Andreas Fault over here. Yeah, so this is a continual process. Okay, so the slippage that occurs along fault zones doesn't happen instantaneously. I mean, it happens really fast, but I guess it's not instantaneously. The initial slip begins at the hypocenter and then propagates outwards. And then that slippage away from where the earthquake begins, or the hypocenter, triggers more slippage, okay? And then the slippage travels kind of mainly in one direction, okay? So the fault slip, this is a measurement of how much movement has occurred on the fault surface. Okay, so here's the hypocenter, and this is the initial slippage where the earthquake begins. This is where the ruptured surface is, okay? And then the ruptured surface propagates at a rate of 2 to 3 kilometers per second. And that's pretty fast, but that's how the slippage kind of propagates along the entire fault surface, okay? And the rupture continues to grow. Here's a fault scarp that forms, okay? Nice little three-dimensional image for you guys to watch. All right, seismology is the study of earthquake waves. All right, these are the geologists that study waves as they propagate through the Earth's crust, and they record them. Okay. The earliest studies of earthquake waves we know comes from the Chinese about 2,000 years ago, and really it was just kind of like like an elephant ornament that had like balls on top of them, and if there was any earthquake, the balls would roll off the ornament. So that's what we're talking about here. But modern seismologists, they use instruments, more advanced instruments called seismographs or seismometers, and they record the movement of the Earth, okay, relative to a stationary rotating drum. Okay, I'll show you a picture of it in the next slide. And so essentially, it's able to measure the crust movement in a horizontal and vertical fashion. Okay, so here's the way one works. One is anchored into the bedrock. Okay, there's a pen and a rotating drum of paper. So as time passes by, it slowly rotates, and the pen just kind of lays on the paper. And if there's any movement here, this would be horizontal movement. If there's a horizontal movement, then the pen will move as a result of it because it's on a pivot. Okay, so if there's more ground shaking in the horizontal fashion, then the pen will go, right? It's kind of like a lie detector test. So every time you say a lie, oh my God. Okay, so it's like that. All right, and this is a seismograph that records vertical movement. It's the same thing, but this time the pen's on a spring. So if there's any vertical movement, the pen will move up and down as the drum rotates, and then it records the magnitude of the seismic waves. Obviously, the larger the seismic wave, the larger the pen stroke is going to be, and it can show up on the rotating drum or the paper as a big squiggly line. That means it's a very strong earthquake. All right, so seismic waves are obtained by these seismograms, okay? And there's two different types of seismic waves, okay? There are body waves, and body waves consist of primary waves and secondary waves, okay? Primary waves have the highest velocities, and they reach the seismic stations first. They're what we refer to as compressional waves. They can travel through all materials, so liquids and solids. Okay, secondary waves are a type of body wave. They're shear waves, okay, and they can only travel through solid material. If a secondary wave is moving kind of through the crust and encounters like liquid, it cannot move through that medium. Okay. Then the second type of waves are called surface waves, and these are the slowest velocity waves, and they arrive to the seismic station last. But these are the strongest seismic waves in terms of ground motion. So this is what causes most of the damage that we see after earthquakes. Okay, so here's an example. This here is a primary wave. If you will, hold out your hand, okay? Pretend that you're holding one end of a slinky, and I'm holding the other one. And virtually, I'm going to give you a Hadouken, right? I'm going to push that slinky towards you, and what will happen is the slinky will compress and expand, okay? That's exactly how a primary wave propagates through the Earth's crust. Remember, this is the highest velocity primary wave over here. This is an S wave. And S waves, they oscillate up and down. So as they travel through the crust, they kind of move in this S shape, up and down. And this is the wave direction as they kind of propagate through the crust. All right, it's kind of like that workout in the gym where you have ropes and you just kind of swing them up and down. Okay, so let's check it out. Look, this is a hypocenter of an earthquake over here. Here are the wave fronts that propagate away from the initial slippage. So here are the primary waves kind of traveling through the Earth's crust. Okay, here are different seismographs in different locations on the surface of the Earth. Okay, and what will happen is primary waves will kind of move along these wave fronts and then come into contact with the seismograph. And then here they are. So the P waves show up first. They're the fastest velocities. Then right behind them are the S waves. Okay. They show up next, and then lagged behind that, the slowest of all are the surface waves, okay, right here. And if you notice, the surface waves, they have the highest amplitude, okay? So this causes the most ground shaking right here. All right, if your seismograph is a little further away, the time lag in between the arrival of the first P wave and the S wave is greater. So this distance increases the further you are away from the hypocenter of an earthquake, okay, along with, you know, the distance between the arrival of the first S wave and surface waves. Over here at seismograph 3, the P waves have arrived. P waves are very fast, but S waves have not yet arrived yet. They're still traveling through the Earth's mantle before they're able to get to seismograph 3. And that's really important. This, the time lag in between the arrival of the first P wave and S wave is important because that's how we determine how far away earthquakes are, okay? All right, surface waves, there's two general motions for surface waves. One causes the ground to move up and down, okay? Kind of like ocean swells. A lot of people that have experienced earthquakes say that they feel like they're on the ocean and they get kind of motion sickness, which is true for surface waves. The second type, this kind of motion causes like a shearing snake motion on the surface of the Earth. Let me show you a picture. There you go. Here's that kind of shearing back and forth. So there's just going back and forth like this. This is a type of surface wave. Very destructive. Okay, kind of shears the Earth back and forth. And then this is the orbital kind of motion, or what the ocean swells would feel like. So as as the surface waves kind of propagate through the crust, you feel like your motion goes up and down as like a wave is passing underneath you, which is bizarre because you're on land. Okay, so here we go. Just to reiterate, P waves, fastest velocities, lowest amplitude. S waves, they're usually second at the recording station. Surface waves are the slowest, last to arrive. However, they have the largest amplitude and cause the most damage. Okay, so here you go. Arrival of the first P wave. We got a little bit of time lag, nothing going on. Arrival of the first S wave. And then arrival of the surface waves. Okay, so how scientists locate the epicenter is essentially by finding out the time difference between the arrival of the first P wave and the arrival of the secondary waves. And they construct what we call time travel graphs. And you can use this. In fact, in your lab, you'll be using a travel time graph and triangulate the location of an earthquake. Okay, so pay attention here. So essentially, let's see. Here's an example of an earthquake that's occurred. We have 3 seismic stations, A, B, and C. Okay. Here's a seismogram in New York, records the arrival of the first P wave. And then here's the time lag between the arrival of the first P wave and the arrival of the first S wave, or secondary wave. Okay. And you can measure this in terms of time. Usually they'll give you, oh, there, that's 1 minute. So it's about, well, let's see, 1, 2, 3, 4, 5 minutes, a 5-minute time lag. Okay. Here in Nome, Alaska, the time lag's significantly longer. So let's count that. 1, 2, 3, 4, 5, 6, maybe what, 6.5 minutes? What that means is Nome, Alaska is further away from the earthquake than New York is. Okay. And if we go down to seismographic station C in Mexico City, time lag is 1, 2, 3, 4 minutes. So actually this earthquake occurred closest to Mexico City. Okay. So what you would do in your lab and what scientists do, this is the time travel graph. And here's the P wave curve, okay? Here's the S wave curve. Remember we measured the time interval, the time lag interval, 5 minutes for New York. So this distance from here to here represents 5 minutes. Here's time in minutes. All right, so just count off 1, 2, 3, 4, 5. Okay, that's about 5 minutes. Here, that distance. All right, so that means if you follow this line straight down, that means that the seismograph in New York is about, let's see, 2,200, 400, 600. Yeah, maybe 3,700 kilometers away based on this graph. Okay, and that's based on the time difference of the arrival of the first P wave versus the secondary wave. And with that information, so you have New York, what did I say, 3,700 kilometers? What you would do is use a compass. Now, I know you're going to be at home and you won't have a compass because we might not be at the lab. But what you can do is here's your scale or a map scale, okay? Use a ruler to measure out what the distance 3,700 kilometers would be, all right, from New York, and then you would plot a point here, 1 point, plot it here, and then you would do the same in a different direction over here, and over here, and over here, right? So that means that the radius of this circle would be 3,700 kilometers. So then just try to draw a circle as best you can around all those points. And what that indicates that the epicenter of the earthquake is 3,700 kilometers from New York. Okay, so the earthquake could have occurred on any point along this circle. Okay, and this is why we call it triangulation, because that's why you need 3 seismographic stations, because you do the same thing to the other 2 places and figure out the distance it is from the epicenter. Nome, Alaska was a little further away, so your circle is going to be drawn a little bit larger, right? And then its circle will intersect with the New York circle in 2 spots, here and here. So those are the 2 possible locations where the earthquake may have occurred, because that's where they overlap. So you kind of created a Venn diagram. And then once you draw the circle with the distance radius from the epicenter from Mexico City, these 3 circles will converge on 1 point, and that point turns out to be right here. So it looks like maybe somewhere on the Colorado Plateau, that's where the earthquake occurred. That's why it's called triangulation, because you need 3 seismic stations, or the data from 1, 2, and 3. So you'll be doing this in your lab and calculating the distance you are from earthquakes from 3 different locations. You draw those circles and they'll all intersect at one point, and that's where your earthquake occurred. Okay, how big are earthquakes? How do we determine how big they are? There's 2 main fundamental ways that we measure the size of earthquakes. The first that was developed in Italy. It's called the intensity. And that's a measurement of how much ground shaking occurred in a particular area. Okay, and it's based on the amount of damage that occurred in the area. Now that's very subjective because you know, if you were like Sound of Music style out there on some hills with no structures and an earthquake occurred, there would be no property damage because there was no property around you. But it could have been a very strong earthquake. Or like there could have been an earthquake in an area where you have a bunch of poorly built buildings that just completely fall apart. That earthquake might not have been that strong, but it caused a lot of property damage, so the intensity would be very high. So the intensity scale is very subjective. Scientists later developed magnitude. It's more quantitative and more objective way of measuring ground motion, and it's based on seismic data. Okay, so the seismic records are used to estimate how much energy was released from the earthquake. Okay, so here's the intensity scale, the modified Mercalli intensity scale. Giuseppe Mercalli developed it a really long time ago. Okay, the values change based on distance from the epicenter. So it kind of helps you figure out where the epicenter is. Let's just jump. Here are the descriptions for the different numbers for the Mercalli scale. Here's an intensity map. There was, I don't know if you remember this, but this was in, there was an earthquake in the Northeast in 2011. Freaked a lot of people out. But there was an earthquake here in Virginia. It was a magnitude 5.8, which isn't that strong, but because the Northeast has bedrock that's made up of a lot of crystalline rocks, the seismic waves propagated and traveled really far distances. So a lot of people felt this earthquake. So here's the intensity map. Okay, what most people felt was a very light earthquake in this region here. Okay, now a similar earthquake, a stronger one, in central California in 2004 was a magnitude 6, and here is the intensity map here. And if you notice, it's not very large. This was more of a localized earthquake, and the reason is because there's a lot of unconsolidated sediment that surrounds the valleys in California, and that kind of doesn't allow the seismic waves to propagate as far, and so not as many people felt the earthquake from very far distances. So here are some intensity maps. Here's a close-up view of that intensity map generated by the USGS. By the way, this is our government agency, US Geological Survey. You can go on their website and basically find out, you know, you can get their app, and the app will vibrate in your on your phone anytime there's a major earthquake on Earth, and then it'll give you all the details about it, which is pretty cool. Okay, let's talk about the magnitude scale, the Richter scale. Okay, Charles Richter came up with it, and it measures the amplitude of the largest seismic wave. And it's a logarithmic scale, which essentially means that anytime you go up in magnitude, that's a 10-fold difference in wave amplitude and 32-fold difference in energy release. So earthquakes, in terms of their size and the amount of energy released, increases rapidly with just one magnitude increase. Okay, so here's, and you'll do this in your lab as well. Okay, so basically, what you find is if you have seismic data, you can measure the amplitude. Okay, so here, this is the largest seismic wave right here. Here's a surface wave. That has an amplitude of about 23 millimeters. And so you would plot a point right here at 23. Then you would find the distance you are to this earthquake by measuring the time lag, right? And we did that in the last exercise. So you measure the time lag, that gives you a distance, and in this case it lets us know that we're about 200 kilometers away. And then what you do is you just connect the dots, and as you connect the dots, you're going to kind of the line will run over the magnitude scale here, and then you can read off the magnitude of your earthquake. And then, so in this case, the magnitude of this earthquake would be 5. So it's based on the amplitude of the largest seismic waves and how far away you are from the earthquake, and then that will give you the magnitude. All right, that's more of an objective way of measuring earthquakes, which makes sense. So like if you have really high amplitudes here, right, and you're very close to the earthquake, if you connect those dots, you'll intersect, whoops, that was a terrible try, but you'll intersect at a higher magnitude, okay? Okay, here's an example of earthquakes that occur, the change in magnitude and the amount of the changing or increasing energy because it's a logarithmic scale. For example, the 6.0 earthquake or the 6.5 earthquake in Loma Prieta, California, YouTube video that I posted within this PowerPoint, that in comparison to the Chilean earthquake was a magnitude difference of about 2. So the Chilean earthquake was about an 8.8. Okay, so that magnitude change was about 2, which means the Chilean earthquake in 2010 was 100 times stronger than the California earthquake. And I'm referring to the YouTube video, hopefully you watched that. And the amount of energy was about 1,000 times more energy released in that Chilean earthquake. So yeah, when you're talking about the Richter scale, magnitude changes really mean big changes in the earthquake, ground motion, and energy. Later, scientists came up with another method of measuring earthquakes because the magnitude the Richter scale can't really measure earthquakes that are really large earthquakes. So they developed the moment of magnitude. And the moment of magnitude essentially measures the amount of displacement that occurred along a fault in an area, okay? And it can also be calculated by modeling data that's collected from seismograms. This is particularly true for earthquakes that are at megathrust faults, so earthquakes that occur in Japan or Chile. Those are the largest earthquakes, right? There was one in 2011 that was a magnitude 9. That was unbelievable, okay? That was the Tohoku earthquake. That one is the largest earthquake in the past 100 years or so. Okay, and we get about one of those, about 1 or less than 1 a year, magnitude 9 and above. Between magnitude 8 and 9, we get 1 a year. Okay, that's a great earthquake, causes a lot of damage. A lot of people die as a result of buildings collapsing on them and problems like that. Between 7 and 8, we get about 15 of those a year. And then as we go down, the earthquakes per year increases dramatically. Okay, so if we're looking at earthquakes with magnitude 2 or 3, that's between 1.3 million and 130,000, right? These are the earthquakes that are commonly generated at divergent plate boundaries. So our Earth is in motion, and that motion is reflected by the number of earthquakes that occur per year, average per year. So this is just a continual process. Okay, so the destruction of an earthquake really is based on a number of factors, and it varies. One is obviously the magnitude of the earthquake. If you have a stronger earthquake, you're going to have more damage. And another major factor is how close people live to the epicenter. The closer you are, the more damage you'll sustain. Okay. Other factors, right? The intensity, how long the vibrations occur. Earthquakes are peculiar. Like if you've ever been in one, time like slows down. Earthquakes typically last maybe 30 seconds at most, like a minute and 30 seconds. But it's like getting into a car accident. I don't know if you've ever had that feeling where you get into a car accident and time just slows down. It just like contracts and you're like, oh my God, I'm getting into a car accident. And then it happens and time goes by real fast. It kind of feels like that with earthquakes. So an earthquake is occurring and your senses are heightened and time slows down as the adrenaline pumps and you're kind of moving on to figuring out how to get out of this situation. So if you have a very long earthquake, that causes more damage. Okay. Also, what did you build your house on? The nature of the material beneath the buildings and structures is very important. If you anchor your buildings directly to bedrock, that's better. Okay. If you're built on sand or loose sediment, the loose sediment that actually amplifies the seismic waves. So the surface waves that approach are amplified, and that can cause even more damage. Okay, and then also the construction practices are probably most important, because if a place is just shoddily built, and it isn't built to a code that can withstand seismic waves that may pass through the area, that's what really kills a lot of people. Okay, here's an image of a building collapse in Alaska after an earthquake. So yeah, soft sediments will amplify the seismic waves. What will happen also if you are in an area um, where there's a lot of soft sediment is you'll have liquefaction. And liquefaction is kind of like what you've been preparing for as a kid your whole life after watching Princess Bride. You know, the quicksand. I still haven't encountered that, but during earthquakes, this can happen. Loosely packed waterlogged sediment can behave as a fluid during an earthquake, and you can actually sink into that. Farmers have claimed that they've lost cows. It's a cow. Okay, terrible. Moo. Because the cows have fallen into these quicksand liquefaction stuff. There are stories of that. And that's pretty sad, because a cow can't really dig itself out of the ground. It doesn't really have hands. Anyways, here are some buildings in Japan that were built on soft sediment. The seismic waves were amplified as a result of that, and these buildings just toppled over. It's pretty crazy. All right, and liquefaction also causes little like sand volcanoes to form. Here's your loose, saturated, sandy material, and when there's earthquake shaking, that stuff can find and rupture upwards, and all this water can spew out with some sand, and then you're left with a little sand volcano. All right, then there are also seashoes. This is pretty interesting. This video is definitely worth it, worth the watch, because it's an earthquake that occurs, and there's like video of a pool, and it basically, when you have an enclosed basin or a lake, water in lakes, or a reservoir, the earthquake waves kind of move that water back and forth, just sloshing back and forth. Okay, and that can be dangerous to boats that are kind of buoyed up against docks. It can have water spill over dams. And so this is a really fun video. I'd recommend watching that. Earthquakes can also cause landslides. Okay, if you have oversteepened slopes and then seismic waves kind of propagate through the crust through those areas, it's going to cause, or it can cause, mass wasting, and that material can kind of come downhill. It can also cause ground subsidence. This is particularly true in Mexico City. There's a lot of ground subsidence as a result of building Mexico City on a lake bed. Okay. Also, fire is a big deal. The 1906 earthquake in San Francisco caused a lot of damage. The waves caused a lot of structural damage to property, but the big thing is about half the city burnt down because the displacement caused a lot of the gas lines to be ruptured, and then those ruptured gas lines caused fires. Those fires spread. A lot of people died as a result of the fires after the earthquake in San Francisco. And to make matters even worse, the water lines were broken, so they couldn't put out those fires. It was a big disaster. Okay. Here, this is the Turnagain Heights example. This was an earthquake in Alaska, and that caused a mass wasting event, or a slide, to occur. If you watch this animation, it's kind of cool. There's a layer of saturated material underneath this pretty nice development in Alaska. And what happened is that as the seismic waves kind of propagated through the crust and came into this area, it caused all this material to move of over 200 meters, and it caused massive destruction. So you can check that out. All right, let's talk about tsunamis. Tsunamis are incredible events, tragic events that occur after an earthquake at a major megathrust fault. Okay, so essentially what a tsunami is just a series of kind of large ocean waves. And it's not like waves that you would see in a movie that are like cresting hundreds of feet up in the air. Typically it's just like just flooding water sheeting and coming in towards land. Um, and so they move very quickly into the ocean. When a tsunami is generated by an earthquake, it moves about 800 kilometers an hour. All right, and then essentially the water just piles up on land and floods an entire area. They can reach heights of 30 meters, which is pretty crazy. So this is what happens. You have the overriding plate, a subducting plate. They're converging, right? So there's a lot of stress involved. And when displacement occurs and there's a sudden movement, think of this as, this is an entire overriding plate, thousands of kilometers in length, moving at once upwards in a certain direction. It's essentially like a giant went into the ocean and just used their arm to just shove water in a certain direction in an instantaneous moment. That creates a huge tsunami wave, and that's what travels in the ocean and approaches land. Okay, so that the strain is released, and that basically pushes water or displaces water. Okay, the first time this happened, not the first time it happened, and we were kind of super aware of it or sensationalized in the news and stuff like that, and a terrible tragedy was in 2004. This is the Box Day tsunami. This occurred on Christmas morning in 2004, or the day after Christmas. So December 26th, there was an earthquake in Indonesia, a very large one, and that generated a tsunami that hit a lot of places in Indonesia, Sumatra, Sri Lanka, Thailand, and this was one of the deadliest natural disasters that has ever occurred. Okay. In 2011, the Tehuku earthquake, that generated a tsunami with, in some areas, had 40 meters high, okay, flooded the inland areas. Watch this video. I'm sure it's footage of the incoming tsunami into a Japanese harbor. Pretty crazy. Here's some pictures of the Sumatra tsunami. All right, this, again, a magnitude about a 9, very large earthquake because it was a subduction zone. 230,000 deaths, super tragic. If you look, it's a lot of places in Sumatra are very flat. They don't have any hills, so nobody was safe. And the tsunami just ripped through this entire area. You can watch this video and see some of the footage of the incoming tsunami. Guys, essentially the population of Orlando is about 230,000. I mean, 270,000, I'm sorry. So just imagine one event occurring and all these people dying, within a couple of days. Just incredible. Here's the Japanese tsunami. You can watch this video. This tsunami reached so far inland and it caused a nuclear meltdown at the Fukushima plant, and they're still cleaning that up today. So tsunamis are very dangerous, and they cause a lot of destruction. Okay, since the 2004 tsunami in Sumatra, we've developed a tsunami warning system, which essentially are buoys that are set out into the ocean to prevent, or to warn people of an incoming tsunami. They do move pretty quickly over the open ocean. Remember I said like 800 kilometers an hour, but the ocean's pretty big. So if there's an earthquake in New Guinea or South America, it'll take about 12 to 10 hours to reach Honolulu. Okay. The reason why, you can't really see it over here, but Sumatra is like an island over here, and then here's like India's over here and Sri Lanka. The Indian Ocean is much smaller, so when there's an earthquake in this region, the tsunami travels in a smaller ocean basin, and those areas are more susceptible to the tsunamis. But they still have put buoys there to help warn people of an incoming tsunami if there's an earthquake. But the rule of thumb is if you're in any of these areas and there's an earthquake and you're by the ocean, go to high ground, because if you go to high ground, then the water won't get to you and you won't drown or be hit by debris or something. Okay, so where do most earthquakes occur? They occur mostly around convergent plate boundaries. Most of the seismic activity surrounds the circum-Pacific belt. Okay, let me show you what that is. All right. This is the circum-Pacific belt. It surrounds the Pacific Ocean. And the reason why there's so many earthquakes here is because there's a lot of subduction. So here the Nazca plate subducting. Here we have movement of the Pacific plate. We have subduction here, here, subduction, subduction, subduction. So yes, a lot of earthquakes are occurring along the circum-Pacific belt. The next major belt is the Alpine Himalayan belt. Okay, and here again, convergent plate boundaries cause, India is moving northward, and that causes a lot of earthquakes to occur all along in Southeast Asia, China, and into the Middle East. Okay, and Italy deals with their earthquakes as well. So this is where the majority of seismic waves are generated. And if you also notice, they kind of outline the mid-ocean ridges because smaller earthquakes occur here as well. Okay, so how can we predict earthquakes? Well, the answer is we really can't. Short-range predictions, meaning like, hey, tomorrow's forecast is earthquake. No, we can't do that. The best we can do, it's impossible to know exactly when an earthquake's going to hit. They kind of always come under surprise, but what we can do is we can measure the changes in ground elevation. Remember, when stress is built up, it causes the land to uplift. You can measure that directly, and if there's more stress, more uplift, that means an earthquake is more likely to occur. You can measure the strain in rocks. If there's any changes in groundwater level, that could be potentially bad. And also, how often foreshocks are occurring. That could be a harbinger of, a major earthquake to come. But the short-range predictions often can lead to failure in accurately predicting an earthquake. Really, there's no reliable method to do this, all right? The only thing we can do are really long-range forecasts. We can say, hey, in the next 30 to 100 years, there's going to be a magnitude 7 earthquake along this fault. Okay, and that might not seem very useful, like, okay, that doesn't tell me anything, but it actually is useful because communities can use that information so that whenever they do any new construction, they can build structures that are able to withstand the earthquake that's inevitably going to come. Okay, the earthquake in Port-au-Prince, Haiti in 2010, there was a scientific paper that came out like 3 years before that earthquake explaining that there is likely going to be a magnitude 7 earthquake within the next 20 years. And it occurred about 3 years after that scientific paper. Okay, so these are useful guides for building dams, roadways, and all that. Okay. Another way of being able to forecast earthquakes is to take a look at seismic gaps, okay, and also take a look at past seismology or paleoseismology. Okay, what a seismic gap is, all right, here is the picture of the tsunami damage in Sumatra that I showed you was right here. This was during the subduction earthquake here in 2004. All right, so the Sunda megathrust subduction zone has had an earthquake in 2004 here, 2005 over here. Now there's been a seismic gap in this region, right? This is the seismic gap region. Okay, and then there was another earthquake in 2010 here, and another one in the year 2000 here. So this entire subducting plate has moved everywhere except this spot right here. That's a seismic gap. So seismologists think that the next big earthquake is likely to occur in this region of the fault because the entire subducting plate has moved everywhere else and is kind of just stuck in that one area. So Padang should really be prepared for the next, magnitude 8 or 9 earthquake, which is inevitably going to happen. So here, this is why the propagating tsunami, as it kind of moved on into India, struck Sri Lanka, India, Southeast Asia, because it's kind of a smaller ocean basin in the Indian Ocean. Okay.